Hi, it's Lab Guy in my lab again. Oh, sorry, wait, no, it's Lab Guy. That was my tribute to Fran's lab. Check out Fran's channel at Fran Blanche on YouTube. Nice lady, going through some rough times right now. She has to move and the construction guys flooded her lab. Just an average day on Earth for your average human beings. Hi Fran, great channel, keep up that good work. I'd like to also give a shout out to my friend Jack over at Vintage Electronics Geek. What Jack lacks in experience, he certainly makes up for in enthusiasm. Great guy, check him out. So, let's get on with today's subjects. In our last video, I showed you the schematics for the high voltage power supply for the Chief, the television monoscope project. Well, for the past 2 days I was constructing the board and it is finished now. Along the way I made a couple of small changes and realized several omissions and errors in the previous video which I would like to address and will get to addressing. So without further ado, let's look at the latest schematic, shall we? Okay, picking up where we left off last time, I began to mention the two filter capacitors on the output of the MCO F10 power supply. I pointed out at the time they were 3900 picofarads, but in the construction I found some slightly larger ones at 4700 picofarads or 4.7 nanofarads, 3 kilovolts apiece. And you might be wondering how a power supply can be filtered with picofarad capacitors. This is a high frequency switching power supply. I don't know the switching frequency, but it is not 60 cycles. So that was the first omission I made. I kind of distracted myself and wandered off subject there. Then down here in the blanking circuit, I showed that the blanking signal came in and was coupled over a capacitor where it was summed with the beam voltage, or more precisely with the grid 1 voltage. So you have the grid 1 DC voltage added with the blanking input voltage. I had the bypass capacitor for that input signal, the grounding capacitor, over here. That was not completely wrong, but it was also not as good as the new arrangement. If you look, we have the input capacitor, the isolating resistor, and the AC grounding capacitor now as a classic pi low-pass filter, RC low-pass filter, so that the blanking input couples across, goes to the grid, but when it feeds back across the resistor, two things happen. One, it's attenuated by the resistor into this impedance over here, this total impedance, and the AC component is shunted to ground by the other capacitor. The next thing that I didn't get into or didn't elaborate on to my satisfaction was about the isolation 6.3 volt isolation transformer for the heating element in the cathode of the tube. I did tell you that I put 1000 volts DC bias onto the heater, totally onto the heater, to protect it from arcing with the cathode. But I forgot to mention that I purchased this transformer specifically for its 2000 volt isolation rating. It is specifically made for this function. Then, after I built the board and began testing it, a normal lab guy thing happened. I know this. For a 12 volt DC input, the LM317 has too much forward voltage drop. It has approximately 2.5 volts of drop from the input to the output under ideal conditions. The power supply wanted 11 volts at the input to give us the 1200 volts on the output. This is a proportional power supply. You can vary the input voltage and control the output voltage. It is an unregulated output. It will actually begin operating at about 0.6 of a volt input and gives like 50 volts out. No current. But the point being that it can be trimmed around its nominal value of 1 kilovolt. The MCO power supplies typically will output their rated voltage at half of the rated current load with a 9 volt input. 9 to 10 volts is what I've discovered over the years. In this case, to get the 1200 out, we had to put 11 volts in. That's a 1 volt drop across my regulator. Not going to happen. So I'm going to change the regulator to a low dropout version made by Linear Technology. It will be replaced by the LT1085 when those arrive sometime in the next 7 to 10 days. For now, what I've done is I've jacked up the input voltage by 2 volts and everything is working. One other thing that I glossed over was the beam control with its parallel 100K resistor. The original calculations that I performed for this determined I wanted a 50 volt drop for this resistor to give me 25 volts of cutoff, not 50. I was slightly incorrect on that. And so the reason there's a 100K in parallel with this beam control was so that all 3 pots are the same type. I could not find 2 100K pots and then a 50K pot that was mechanically identical. I think it was a case that the 50K pot was pretty close but had the knurled shaft for slip-on knobs, and the other 2 had the D-shaped shafts for the set screw type knobs. Not acceptable. I'm not going to have garbage knobs on the front of this project. So that pretty much takes care of all of the oversights and straight out errors on the last video. Since then, I also added an LED to the board that tells us that the high voltage is on so that I don't stick my fingers in there while it's running. So, enough about the schematic. Let's take a look at the brand new board. And as usual, at the end of this video, I will post the schematic for your enjoyment. Okay, here is the finished product. It's constructed in such a way that the controls can be are off-board and will mount to the panel. When this board is mounted in the cabinet, it will actually be mounted upside down in the box. This is the front view. Let's go over the highlights of the board. Here's the DC switching relay with its flyback diode. The 6-pin input header, which brings in 12 volts DC, the relay drive signal, and 2 pins going out for the remote LED that will be on the front panel. Here we see the LM317 regulator, which will be replaced by the LT1085 shortly. Over here is the voltage dividing resistors, the 2 4700 picofarad filter capacitors. Over here is the filter that I showed you for G1 for the control grid, and its 2 capacitors and its 4.7K resistor. connections to the high voltage are soldered connections. The low voltage can be on a plug. If I'm moving the thing, take it in the car somewhere to show it, and the plug falls off the low voltage side, no harm done. I just plug it back in. If one of the high voltage wires come off, who knows what damage could be done, so I have a rule that those are soldered. When I build my boards, I make these little wire loops out of 22 gauge copper bus wire, which I bend over the back side of my tweezers into these little loops that stand up about 3/8 of an inch from the board. They have a drop of solder at the top of each loop where the wires can be quickly attached and detached. It's very convenient, and I learned this at my previous job in a Silicon Valley IC company, who will remain nameless. So, on the right side of the board are the three pots, the shading control, the focus control, and the beam control. Along the bottom edge of the board here are the connections that go to the monoscope tube base. We have the collector ring, the second anode, the first anode, the focus electrode, the cathode, and grid 1. So those 5 wires emanate from right here. The remaining 2 loops are the blanking drive input for the negative going blanking pulse, which is AC coupled through the bottom capacitor and summed with the bias voltage from the beam pot through this resistor. That occurs right here. And over here, as an afterthought, I added an LED that lets us know the power is on. So let's fire the board up now and take some voltage readings and see how well it's working. So the first thing we'll do is connect up the low voltage power supply to one of the 3 ground pins, doesn't matter which, to the 12 volt input, which is currently being driven with 14 volts. I have temporarily placed a small jumper plug across the 2 middle pins, which are the relay enable, so that the board will power up. Next, we want to hook up the ground of our meter, and conveniently the A2 pin, anode 2 right here, is ground. High voltage ground. Well, it's system ground. So we will connect there, and we will connect the meter's positive lead to the cathode. Because if you remember in my description, we set the voltage between anode 2 and cathode for 1000 volts. The meter is connected backwards, so it will be negative 1000 volts. We power up, and we are seeing 880 volts. We can adjust our LM317. I use a 10-turn pot to make precise setting a little easier. It's still kind of touchy. Perhaps in a later update I'll pad that out with some resistance to make it less touchy. But we dial it until we get to minus 1000 volts from cathode to anode. Or I should say anode to cathode. There we go. 1001 is pretty good. These pots have some backlash, so when you overshoot, they're a little hard to back up. There we are. We're within less than, well, we're right on. There's 1000 volts for our electron gun. So, looking at G1, which I've never done, so let's see if it works. It should be negative. 1025, 1022 is good. the focus electrode, which is the minus 670 that we saw in the test setup before. So our voltages on the output side are good. They're within range. They're all reasonable. The collector voltage should be 50 volts. Well, it's not because I don't have the pot centered. And I really don't want to get bit. Okay, 50 volts. We'll call that 50 volts. Everything is working. Now we go over to the regulator DC to see what the input voltage to our MCO power supply is. And it is 11 volts. So for 11 volts in, we get 1200 volts out to drive our chain, and everything is working. So the new board, number one, it works. Number two, it's beautiful. And number three, I can now move on to the next thing we need to work on in the project, which will be the horizontal scan board. I've ordered some proper horizontal output transistors. I've been using a audio output transistor intended for line operated products, so its maximum voltage rating was only 120 volts, and it's probably not ideal for the function I was pushing it into. I copied someone else's circuit. So that's where we're at. The Chief is moving along nicely now, and hopefully within a couple of 3 or 4 weeks we will have a whole unit we can begin testing. I still need to build the video preamp, the video post-process amplifier, and the deflection system, which is still being worked on but is coming along nicely. But I had to switch to something else for my mental health because I was becoming too frustrated. So this is where we're at. Lab Guy out.